Suppose you have been given the task of providing water to the city shown here. This city is surrounded by several options, including the 2 rivers and the 3 lakes to the northwest. The challenge to providing water to a given area is that by providing water, we must also provide energy. The same energy that ensures when the tap is opened, there is enough pressure to allow it to come out of the system we design. Therefore, the first question is, which of the sources will provide sufficient water and sufficient energy? To answer this question, we need to decide how much energy is enough for the residents of the city to make use of the water. Arbitrarily, let's say that our city needs at least 30 pounds per square inch of water, of pressure, for the water to be usable to the user. We can express 30 psi in terms of elevation. The conversion is made by calculating the number of square inches in a square foot, then dividing by the unit weight of water. In other words, for every psi, there is 2.307 feet of pressure head. If we want to express 30 psi in terms of head, then we multiply it by the conversion factor to get 69.21 feet. Because this calculation does not consider friction losses, merely the elevation difference and the weight of the water, this is referred to as the static head. Using 69.21 as the minimum static head, we can consider what elevation corresponds to this value. So starting from the highest elevation in the city, we add on the minimum static head we just calculated. Then we draw a line horizontally over to the elevation along each of the rivers to determine where we can tap our water source. What elevation along the river should we start our water supply system? Take a moment to figure this out yourself. This may seem like an odd exercise, but in the days before electricity, this is what the great cities of the Roman and Turkish and Babylonian empires did. Rome, which is the city represented here, then would tunnel through hills and bridges over valleys to deliver the water to the city via aqueducts. As another example, suppose we want to tap lake number 1. We can use our conversion factor and the elevation of the lake and the city to determine the maximum static pressure supplied by this source. Since we are interested in the maximum static pressure, this time we use the lowest elevation from the city. To take a moment to calculate this value as well and tell me, do you think this value is too much? Within a given water system, we try to manage the energy in our system. We neither want too little or too much pressure. Too little, and the water is of little use to the end user. Too much, and it can damage our distribution systems and even the plumbing of our homes. For this reason, a water agency must establish a static head criteria in order to limit the pressures within their system. Even though each agency can decide the minimum and maximum pressure, there are typical values used by most agencies. Most set the maximum static criteria between 100 and 120 psi, while on the low end, values between 45 and 60 psi are typical. Given the elevation of a water source, there is a maximum and minimum elevation that can be serviced so that the pressure stays within the static pressure limits. In the figure shown here, the elevation of the lake is at 850 feet. If the lowest pressure is 50 psi, then we can determine the highest elevation where homes can be serviced by subtracting 50 psi from the 850 feet of head supplied by the reservoir. Likewise, if we want to limit the maximum pressure in the system to 120 psi, then we subtract 120 psi from the lake elevation. Like this. The static head criteria is one of the main considerations when defining the service area of a water distribution system. These 2 elevations provide the city a hard limit for where new homes or shopping centers can be built, all by just quantifying the static energy of the water within the system.